Thank you for the introduction. Good afternoon, everyone. My name is Ray Yu. Today, I'd like to introduce our recent work, nanoPI, Extreme Scale Actively Secure Multi-Party Computation. This work is done with Dan Cassell, Amr Sabri, and my advisor, Yan Hua. There's significant progress in practically actively secure multi-party computation. Last year, the author of these two WK papers launched a global scale experiment with up to 128 parties. This work improves the state of art to a new level. The rest of this talk will be based on this WK protocol. Your researchers test several applications, including AES, SHA-1, and SHA-256. The size of these applications range from several thousand gates to tens of thousand gates. An immediate question is whether the protocol scale up to larger circuits. Well, there's still a big gap between the state of the art and the real-world demands. The typical application size explored still at the 1,000-gate level. For example, SHA-256 contains only 91,000 gates. However, the real-world applications are way more larger. For example, machine learning algorithms contains at least billions of gates. A tiny example is logistic regression, 1,000 MINST records. The size of this logistic regression is 4.7 billion gates, which is 50,000 times larger than SHA-256. Besides machine learning, many other applications are still well off the chart of existing benchmark applications. For instance, at the distance between two DNA sequences with only 2,000 nucleotides has a scale of 340 million gates, which is 3,500 times larger than SHA-256. These real-world applications are not really large at all. It takes only 2 minutes to execute this logistic regression. It takes only 12 seconds to execute the edge distance in plain signal circuit. If it is executed in instruments, this computation are only second level. So can existing constant run protocols scale up to real-world size? Or they can't. The space requirement is too high. In constant run protocols, memory demand is huge for relatively large applications. For example, logistic regression takes as large as 16 terabytes to execute in two-party setting. Even computing the edge distance of two DNA sequences has a memory demand of 1 terabyte. In contrast, the explored range of the applications is very limited. Even with Tier 1 machines, the largest circuit we can execute is only 16 million gates, even though sorting only 6,000 integer is off the table. If we only have a everyday laptop with only 8 gigabytes memory, then mainly 25 SHA-256 will be on our reach. If the device is something mobile, for example, your cell phone, with only 1 gigabyte memory, 3 SHA-256, well, it's gone. We can see that in two-party setting, even small-scale real-world applications are well beyond the reach of existing solutions. That's only in the two-party setting. For n-party case, a multiplicative factor of n-1 will apply to the memory demand. That's to say, the gate cap posed by the memory limit will shrink by a factor of n-1. The situation is only getting worse with more parties involved. So why would constant run protocols take so much space? Well, in the actively secure scenario, processing each batch of gates requires a constant run in offline setting. So does the online phase. To achieve constant run property, one can only afford one offline and one online phase. That implies that he has to store the whole circuit as processed offline. A naive solution is to reduce the batch size from the whole circuit to one gate. Then we don't need to store the whole circuit at all. This doesn't really work. It induces at least one round trip per gate. Suppose we are executing skew computation between here and Chicago. The distance is about 700 kilometers. The speed of light can only travel less than 250 rounds per second. That means such solution can't execute more than 250 gates per second. It sucks. Now we have seen that a naive solution may have small space demand, but it has too much time to run. In contrast, the state of art is fast, good, but it has huge space demand. It seems that we have to choose between huge space demand or huge running time. We are trapped in this space run dilemma. The question is, can we find a way to configure the protocol according to the user's budget to achieve the best performance? Can we achieve both space efficiency and time efficiency? This work provides a positive answer. In this work, we revealed and analyzed the space run dilemma. We resolved this dilemma with light-weighted program transformation techniques. This technique may be of independent interest to scale up other protocols. We also developed a multi-party computation framework, nanoPI, based on the WK17 protocol. nanoPI provides extreme scalability. We execute about 41 billion ends within less than 400 megabytes space for 4-party setting. Not like other existing constant run protocols, nanoPI works in resource-limited scenario. Besides, it's easy to write applications in the C-like language we defined. This is our workflow. The user specifies the application using the C-like language we defined. nanoPI will use a static rewriter to add instrumentations and to produce instrument code. We also provide instrument functions to help the execution, crypto backends to run the underlying WK protocol, and some basic circuits like fixed-point arithmetic. We feed all these components to an off-the-shelf compiler to generate the executable. Here are some examples demonstrating the scalability of nanoPI. With the loss of generality, we focus on the 4-party setting. The scalability of original WK protocol is quite limited. There's a 2 million gate cap even with 8 GB space budget. If the space budget is shrink to 200 megabytes, the gate cap reduced to only 38,000. This is not enough for SHA-256. In contrast, there's no circuit size limit for this work. It can scale up to arbitrary size with very limited resource. In general, nanoPI can execute an infinite number of gates with small space and preserve the performance of the state of art at the same time. For example, 50 megabytes is sufficient for 2-party setting, and 150 megabytes is sufficient for 4-party setting. Now let's move on to the technical details. First, let's examine the factors that contribute to the huge space demand. There are 4 major factors: gobble gates, multiplicative tuples, circuit files, and whiles. Pipelining technique can reduce the space demand of gobble gates to a constant. Pool technique can reduce the space demand of multiplicative tuples to a constant too. Let's quickly go over the pool technique. We generate leaky end tuples and check them with a fault detection rate of 1 over 2. Then we collect these leaky end tuples to form a leaky end tuple pool. Leaky end tuples in this pool will be randomly picked out to combine to remove leakage and used in computation. Once the leaky end tuples in the pool are consumed, we will generate new leaky end tuples to refill the pool as soon as possible. Now, let's focus on reducing the space demand of the rest 2 factors, the circuit file and the whiles. A strongman solution to reduce the space demand is to use many circuit files instead of a huge one. Can this solution work out? Well, suppose we have a huge circuit of 1 billion gates. We could generate small circuit files dynamically so that none of them is too large to store. This approach may reduce the space requirement for the circuit file to a constant. However, this is far from being satisfying. There's a serious issue. Suppose this AND gate produced a while, number 1,030,000. The question is, when do you free this while? Well, that depends on when is the last use of this while. It can be used here or here. We don't know. In general, it's hard to answer this question, so we can't safely free this while. This unfreed while will eventually eat up the purchase space budget. The circuit file attempt doesn't work out. So we switch to another approach. We use programs instead of circuit files to represent the applications. We also use program instrumentations to manage the while release. Here is the example of 8-bit marks. There are several issues to note before getting the code ready to use. Note that our undying protocol has runs during the online phase. This is also the case for many other protocols. They are suffering for the same issue. In the original protocols, all the gates are executed in one huge batch to reduce the round trip. However, in nanoPI, we execute the gates in many smaller batches instead of a single huge one. Therefore, when the gate will be executed depends on space budget and the concrete circuit structure. Since the execution of the gates are delayed, new implementation issues raise. First is overwriting. Let's see some examples. Can we overwrite the value of this t? No, because the execution of this AND gate is delayed. Similarly, can we always overwrite the old value of this t? The answer is still no, because this AND gate and the XOR gate could be packed in the same batch, so we cannot do overwriting. Besides, look at this chain expression. These two gates is possible to be packed in the same batch. That's to say, the result of this AND gate is unknown until it is a delayed execution, so we cannot process the XOR gate. Besides that, scoping rules are also very tricky. Can we free this local variable t when exiting this scope? No, because the delayed execution may not have been triggered when we exiting this scope. So to overcome all these challenges, we combine the static and the dynamic instrumentations so that whiles correspond to memory objects that are dynamically created and deallocated as needed, and gates are automatically packed into batches. Now let's see a 2-bit marks as a tool example to demonstrating how we free the variables. Remember that the bit variables here are no longer really whiles. Instead, they are merely pointers to the corresponding memory object. We manually insert instrumentations. There are two instrument functions, release and release array. They don't actually free the variables. Instead, it only marks the corresponding while as destructible. Now let's see how this instrumented code is executed in the backend. During the execution, in addition to the variable states, we also have a gate queue to note down the delayed gate and the whiles to note down the destructible while. At the beginning, the inputs are loaded in, the whiles are stored in the manually managed memory area. The variables are only a pointer to the corresponding memory object. Then we zoom into the first max function. Instead of immediately executing the gate, all the gates we encountered are pushed into the gate queue. First is this XOR gate, followed by the AND gate. Then we encounter the release instrument. The pointer is described immediately, but nothing happens to the while for now. We only mark it as destructible. Then we continue to push gates into the queue. After that, we encountered another instrument. We destruct the pointer and note down the corresponding address. Then we zoom back to the main function and zoom in to the second max. The first XOR gate in this max will be pushed into the gate queue. At this moment, you can see the gate queue is full, and then the real execution is kicked off. This is the point at which the network traffic and heavy computation really start. Gates in the gate queue will pop and execute one by one. Both the whiles with or without the destructible mark could be used as the input while and output while. The output whiles will be updated according to the gate. After gate queue is empty, we deallocate all the destructible values. After emptying the gate queue and free all the destructible values, the real execution paused for the moment. Then we continue to run the application. We push this AND gate encounter into the queue. The instrument destroys the pointer and marks the while. We push another XOR gate into the gate queue. When exiting a scope, we mark the variables we declared in that scope as destructible unless the variable is used by the return function. This rule applies in both the max function and the main function. At this point, we have reached the end of the program. We will kick off the last batch of real execution. Like we have seen, gates in the gate queue will pop and execute. All two whiles will be updated. After the gate queue is empty, the destructible whiles will be deallocated. After that, our execution is finally finished. We have formally proved the correctness and space efficiency of our program transformation with programming language techniques. Our code is available on GitHub. In this work, we combine the programming language techniques as well as the multi-party computation techniques to produce an actively secure multi-party computation protocol that can run infinite size of circuits, and it uses small space, and is run as fast as the state of art. Thank you.
Again, we've lost a few questions. Marcel?
Hi, yeah, quick one. Maybe a bit of a philosophical one. I would say in classical computation, like you can find a computation that takes more space than x for whatever x is. And I think this sort of contradicts, like seems to contradict, at least on the surface, your claim that you can run any computation with limited space.
Yes.
Do you have any thought on that?
Yeah. On our okay, so maybe you need a space to store your workspace. So basically, our space consumption is only a constant factor of plain text signal.
Okay, thank you.
Why do you annotate the release as opposed to using like static, scoping rules? It seems like that information is already available.
You have seen this slide.
Yeah.
So
releases.
Because this release, when you actually scope the local variables in the original C interpretation, it should be released, right?
But I mean, you can just like schedule. You can use it going out of scope to schedule your future release on the back end.
Okay, so the thing that we don't rely on the original C release scheme because it is not met our requirement.
I'll ask a question similar to Marcel's. How do you run programs that require infinite circuits? You used it on your slide. Maybe we find the slide that says infinite something. Oh yeah, infinite size computation.
Infinite size. For example, you can write an infinite for loop to execute AND gates. That's a way to execute literally infinite number of gates. But in practice, you can execute as many gates as you want with limited resource.
I guess you don't really mean it. Maybe you mean unbounded.
Yeah.
I don't know. Okay. Any other questions? There must be some. We have lots of NPC people in the room. This is your opportunity. Okay. Then we'll thank the speaker again. Thank you.